right, let's continue. I hope you have been able to reproduce this. So now the next step for us is gonna be controlling the flow of it. So in order to control the flow of it, the first thing that we need to do is to replace, as we did with the vanilla one, is to replace that for some useful memory addresses, right? Because as it is right now, we have replaced the structure exception handlers for arbitrary values that was A, B, 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 D, 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 so basically 43, 43, 43. But now we want to replace it for something that is actually useful for us. And what do we need to do in order to control the flow is to find a way to jump back into the stack. And why do we want to jump back into the stack is because the stack is where our values are, where our data is. So in order to do that, we need to find a jump ESP. That's jump to stack, right? Or pop red, in order to go back into the stack. Because remember, we are coming from the stack, going into. So first we are in the stack. Then from the stack, we are going into the exception value. And now what we want to do is to go back into the stack. Because there is that's where our values are, right? This. So in order to do that, we need to replace the structure exception handlers for a pop red in this case. That's what we're gonna use. And how do we find pop reds? So this, by using the script that I showed you before, the plugin, and we're gonna call. So basically, we're gonna look for memory addresses that contains these opcodes in the memory space of the application itself. So run the application, and then go to log ERC. And then from the commands, from here, we're going to use this one. We could also do a search memory, but let's use SEH. So SEH command. Sorry guys, I'm going to sneeze. There you go. Yeah, I didn't want to sneeze on the microphone, so I muted myself. All right, so we're gonna use SEH, and this command is gonna display a list of addresses for pop red instructions. So if we are in a vanilla exploit, jump SP is gonna do the same for us, basically going back to stack. Because we are on a SEH exploit, we want to do pop red in order to go back to the stack. So SEH is gonna pop red, and then that's what we want. Let's press enter, and then you have to give the plugin a while, and then it's gonna show all the memory addresses that contains pop red instruction. Of course, what you want to do is to pick one memory address from here, from this list, that will be in the same memory space of the program itself. So you can pick this one, for example, from SH core, or from EMM32.dll from system32. But what's going to happen is that this, if you pick one of these, is going to depend on the platform that you are running it from the target, right? So if I create an exploit and then it's abusing this memory address, or maybe not abusing, but using that memory address from this DLL, the binary is going to call always this DLL, but the DLL might change, right? So then it might not be there, that memory address, or it might not, or it depends if there is a protection that is changing the memory address space, or directly it's a new version of the application of this application of the within this DLL. Then that location might be corrupt or might not be there or might be called to something different. So that's why, preferably, if you can, always pick an address from the binary itself. So then this is basically return-oriented programming. So what you're gonna do is you're gonna return back into the program itself instead of jumping into something else. You're gonna jump, you're gonna run something from the program itself, and what you're gonna run is quite simple: is pop red. Yeah. So let's pick one. Let's say this one. Here I have one different. Yeah, because I choose that one once all the DLLs have been loaded. So let's do that. Let's actually do that. So let's run it. We have to trigger the overflow, and then you can see the difference. So we're gonna go into crash, trigger the overflow, and then we're gonna run this script again. So we go there. We see in the log the access violation, and now we're gonna look for SEH. Gonna take some time. There you go. And now, as you can see, there is a difference with the DLLs that have been loaded, because remember, these DLLs are dynamically loaded. So once the program is running, these DLLs are the ones that are loaded at the point that I have triggered the overflow. So all these DLLs can be used. But as I mentioned in the beginning, of this topic, we should pick one that is part of the main program, because that one is not going to change, right? So that's why in this case, I have picked, if I go to the exploit, this one from RLA pack.dll, because that one comes in the bundle. So it should be any of this. And if you don't want to scroll to this, you can also go into the log. I have two, because this one is the first one at the beginning of the program, and this one we executed at the time of the exploitation of the trigger, right? So these are the most safest one to use, because these are part of the binary itself. But I will say that it's safe to use the DLLs from that come bundled with the binary. That should be safe to use. But let's say we want to use this one. So that's a base case scenario, one of the binary itself. So we copy that one. We're gonna put it here. We're gonna replace it, and then we're gonna say this one is. CF 72 61 oh. So Indianness, we do it in reverse. OE 61 72 CF. Now we need to restart the program, run it, and then as you can see, I have uh, two exceptions. Two exception handlers, right? Because this one is going to jump into the this one is going to jump into the stack. It's going to do the pop red, but then I need to jump. I need to go over it, otherwise it will keep on going. So in order to jump into it, I need to use EV OB. That's basically the opcodes for short jump. So that's a short jump in assembly. And then I'm adding, that's what I'm gonna run. And then I'm adding 9090 as a filler. So 90 stands for no operation. So it's the in assembly is gonna be short jump plus no operation. Uh, it's gonna be like that. So short jump plus no operation. So the assembly, the opcode representation is EB OB, right? Plus 1990 choose to fill it. So this is the value of the pop-up red. Then this is gonna be executed, and then it's gonna run. So let's try it. So if we run this, go to crash, go here, and then you can see the trigger and follow the flow of the handlers. So first, it's gonna trigger the overflow. So first crash because we have reached our ace. Remember, after 200 something, we can actually check that because we have it here. So the instruction pointer has been overridden after 292 A's. So that's why 292 A's. So actually we can say 292. We can actually put this. So we need to do 7, 20. This is not needed, but it's just -4, of course. Gonna be 88. Now, instead of 41, 41, 41, it's gonna be EIP. When I restart it, crash, need to continue execution with model, edit, we paste it. And then if you go there, oh, we need it. We haven't done right. It should be correct. I guess not. Something else. Pop red. Run it. Mhm. Now we did something wrong. But we have it here. Let me check. We did it. The vanilla one was right. Yes. We can check on that. Yeah, 292. And then this. Oh, it was 292, of course, guys. Did someone already notice that on the chat? Tell me now. Okay, so it was 292, of course. Yes, so it was 202 after 292. Then we have the DCBA. Then the total it was 1,000. So it's 202 plus 4. And here we need to take 4 out because we are adding this, right? So this is 4 bytes. So this is gonna be 188. Let's check it. No, 186. Check it. And if we do it right, then it's gonna be 292 plus 4 plus 216 should be 1012. Yes. Then after 1012, we are adding this to the first exception handler. Then we are adding this to the second exception handler. And then our filler. And then we run it. Take the crash. Let's run it again. Now copy our buffer into here. There you go. And now it should be yes, 41, 42, 43, 44 as the value for EIP. And now if we press F9, we're gonna see what should be already there. We're gonna see it. So that's our jump. So go here, we see here our jump, your jump. Continue. And now the your jump landed there. Now, if we continue, we see here, that's where we land. So now we want to jump into something that is actually useful because this is not something that we can if we can use, right? So what we gotta do is to replace that jump for something that we can run into. So let's actually do that. So that's why we're gonna use a shellcode. But first, before using a shellcode, let's replace the buffer for so you can see it actually running for 290s. So we need this and this. We're gonna take it away so it's more clear. I'm gonna run it again. So we're gonna step by step so you can see how it works. Oh, so something wrong with Python. And this part very easy. We can try it with the Python interpreter and see what's missing. Shellcode is not defined. Of course, we don't have to remove it. So we're gonna choose only write the buff. There you go. Let's copy this, run it again, and then we can follow up until we reach our knobs. Remember, no operation. Knobs stand for no operation. So first we reach the instruction pointer here. Next. Then we are going into the exception. Here our pop red, you see here. So that's where we are jumping into. Pop, and then red. And then we reach the short jump. So this, the short jump, and the short jump is gonna jump over this, and it's gonna reach the knobs here. And then continue execution. And now we are executing knobs. Okay. And now, oh, I cannot control set. Okay, no, doesn't matter. What we need is a shellcode. But did I choose remove the shellcode? I can take it from the exploit. All right. Let's just make this shellcode here. To fix the identification. All right, so now what's going to happen is we're going to add the knobs, like a lot of knobs. We can fix that, and then after the execution of that knobs, is going to execute our shellcode. Our shellcode is basically a system call to calc. So let's run, and that's going to be the full exploit. Then we can start modifying this exploit a little bit to make it like that. Yeah, to make it a little bit better. So copy, run. There you go. Now this has been triggered. We are going into instruction pointer 41, 41, 41, 41. Trigger the exception, press M9. Now is going into our first exception handler here. Then to the jump. And we can see here, if we go into the SEH chain, here's a jump. Then if we continue, so now we are here. If we continue, the knobs have been executed, but I went one step too far. So instead of pressing F9 and continue execution, I want to show you the knobs. So let's go back again, do it like that. So we go there. So 41, 41, 41, F9. We reach the first exception. We are here on pop red, pop, red, and then press F8, and it's gonna go, the return is gonna go into our chump because the pop-up red is taking us to the stack. And then from the stack, we are executing this already from the stack. Sorry. So we are executing the short jump directly from the stack. F8 to the stack, and now we are jumping into this amount of A's. That is 3000 minus 1012 minus 8. So that's a big amount of A's. So 3000 minus, wait, 3000 minus 1012 minus 8. So it's minus 8 is because of this. So it's 4 bytes, 4 bytes. And then 1012, that's chunk. In order to reach this, we need 1012 because that's the offset that we need to use in order to write the SH. Then after that, there's amount of knobs, no operation, is gonna get executed. So if I press F8, I continue the execution. Now I'm running my code, but the code is just no operation code. So what I can do is, well, I can I can put a little bit less of an operation, or maybe can add a breakpoint. Yeah, I'm gonna add a breakpoint into the last node. So if I continue that execution, I'm gonna execute all those nodes until I reach here. Now I'm here. And now if I continue execution, it's gonna run my shell code. This is the shell code. That's basically this shell code is basically running a system call to execute the calculator. And then the program is running the calculator. Let's fix this a bit with what we have done before on this one. So we were using this memory offset here like that. So that's gonna be the filler. I mean, we can also let's put it here instead. What we can do is to reduce the amount of knobs. That's a bit too much. Yeah, EIP. Then we say 4 bytes, 4 bytes. We are using this one. So this is it's like that. This is gonna be one. This is gonna be junk. This as well. Chunk. Then we have 4 bytes. 4 bytes. The jump short. The what we are using now, RL pack. It doesn't matter. You need a pop or red. Then we're gonna use the filler, the shellcode, and we need to write the buffer plus the shellcode. Otherwise, it's not gonna work. Let's move that. Shellcode. Yes. All right. Yeah, let's try to reduce the amount of knobs, but it should be knobs instead of these. That's gonna be knobs net. And let's do 1000, 2000, a bit less. Let's run it. right? Okay, that's our instruction pointer. That's the pop red here, this one. Now the pop-up red is gonna take us to the stack. Now we are on stack. And from the stack, we are going into this. Actually, we can get up way less knobs. I think we can do with 16 or something like that. With or maybe less. Let's actually rewrite with way more, way less. Okay, instruction pointer, continue. That's our pop red, jump, and now is to if the jump has 16 is way too less. So we'll see how what happened. So now instead of jumping into knobs, now this is disaligned. So we need more than 16. See? So I added 16 minus this amount, but now it's way too less. So we need more. So see, if I continue execution, now the code is corrupted. So let's we could have counted that, but let's add 64. And if we wanted to, we can be precise with this. Pop red. No, it's also way too less. So let's just keep it let's keep it big. So we don't have to on this, or we can be precise, but it's for the sake of the exercise. And also to show you how to debug. How to debug it if you have a problem, how to adapt. How to adapt the code, right? That's what I meant. Go here, there, okay. Exception, pop-up red. We're gonna keep it on 3000. Can be less, but otherwise we're gonna have to start counting. And actually we can because we already know it's gonna work, we can run it outside the debugger. I can also show you outside the debugger how it works. You remember it should be this one, GUI, and this should pop up the calculator. So outside the debugger, of course. But now you see how changing the values, we are adding stuff, we are adding and modifying stuff that is actually not needed for the exploit itself, but just to have more clear a way of seeing how this exploit works. So that's I'm gonna share later with you the exploit code, but you can let me share the let me see if I can share so you can try it on your machine, the exploit that we are trying. And then after you have tried this exploit your machine, what we're gonna do, we're gonna jump into close this. We're gonna jump into the Echat server. So basically another SEH exploit, but it's gonna be remote. So you can see the difference. That's basically the same concept, but instead of sending it the client side, you have to send it to a socket. All right. So we'll share this file with you. Say this one. There you go. So try it. Check if you can pop up the calculator on your lab environment. And if you want to try something out, you can change the pop-up red to something else, or also change PCBA for something else, just for the sake of it. I'm gonna give you a few minutes to try this out, and then we're gonna jump into the remote exploit.